Space is vast, time is fleeting, yet nothing is more mind-boggling than a paradox that can shatter the foundations of logic itself. Imagine a statement that contradicts itself, creating a logical loop that seems impossible to escape. This is the realm of Russell's paradox, a mathematical puzzle that has captivated thinkers for over a century. Prepare to enter a world where sets, those fundamental building blocks of mathematics, become entangled in a mind-bending contradiction. Our journey begins with a seemingly simple question. Can a set contain itself? At first glance, the question might seem absurd. How can something contain itself? Yet, as we delve deeper, we'll uncover a truth that is stranger than fiction. Russell's paradox isn't just a mathematical curiosity, it's a profound insight into the limits of logic and the surprising ways in which our intuition can lead us astray. Before we confront the paradox head-on, let's take a step back and familiarize ourselves with the basics of set theory. Imagine a bag of marbles. This bag represents a set, a collection of distinct objects. The marbles are the elements of the set. Sets can contain anything, numbers, letters, even other sets. In set theory, we use curly braces to denote sets. For example, the set of even numbers less than 10 can be written as 2, 4, 6, 8. We can also describe sets using rules or properties. For instance, the set of all even numbers can be defined as x, such that x is an even number. Set theory provides a powerful framework for organizing and understanding collections of objects. It's a foundational concept in mathematics, underpinning everything from basic arithmetic to advanced calculus. However, as Russell's paradox demonstrates, even the most fundamental concepts can harbor unexpected surprises. To grasp the essence of Russell's paradox, let's imagine a small town with a peculiar barber. This barber has a unique rule. He shaves all men in the town who don't shave themselves. Seems simple enough, right? But here's the catch. Does the barber shave himself? Let's analyze the situation. If the barber shaves himself, then he violates his own rule because he's only supposed to shave those who don't shave themselves. But if he doesn't shave himself, then he must be shaved by himself, according to his rule. We've reached a contradiction. This quirky scenario, known as the Barber paradox, is a clever analogy for Russell's paradox. It highlights the absurdity that arises when we try to define sets that contain themselves based on self-contradictory rules. Just like the barber's rule creates a logical loop, Russell's paradox reveals a fundamental inconsistency in naive set theory. Now let's translate the Barber paradox into the language of sets. Consider the set of all sets that don't contain themselves. Let's call this set R. Now the crucial question arises, does R contain itself? If R contains itself, then it must satisfy the condition of not containing itself, which is a contradiction. On the other hand, if R doesn't contain itself, then it should be included in the set of all sets that don't contain themselves, which is R itself. Again, we arrive at a contradiction. This is the essence of Russell's paradox. The very definition of the set R leads to a logical inconsistency, demonstrating that not all describable collections can be considered sets. The paradox challenged the very foundations of set theory, forcing mathematicians to re-evaluate their understanding of these fundamental concepts. Section 5. Shaking the Foundations. The Impact of Russell's Paradox. Russell's paradox sent shockwaves through the world of mathematics. It revealed a fundamental flaw in naive set theory, which had been considered a solid foundation for mathematics. The paradox demonstrated that not all collections that we can describe with words can be considered sets without leading to contradictions. The discovery of the paradox had a profound impact on the development of set theory. It led to the development of axiomatic set theory, which aimed to rebuild set theory on a more rigorous foundation. Axiomatic set theory introduces a set of axioms, or self-evident truths, from which all other set theoretic principles can be derived. These axioms are carefully chosen to avoid the inconsistencies exposed by Russell's paradox. The impact of the paradox extended beyond the realm of pure mathematics. It raised fundamental questions about the nature of logic, language, and the limits of human knowledge. The paradox served as a stark reminder that even our most fundamental assumptions can be flawed and that the pursuit of knowledge is an ongoing journey. Section 6. Beyond mathematics, the paradox's reach into other fields. The ripples of Russell's paradox extended far beyond the confines of mathematics. influencing fields as diverse as philosophy, computer science, and linguistics. In philosophy, the paradox fueled debates about the nature of language, self-reference, and the limits of human understanding. In computer science, the paradox has implications for the design of programming languages and the development of artificial intelligence. Just as naive set theory led to contradictions, poorly designed programming languages can lead to logical errors and program crashes. Understanding the principles behind Russell's paradox helps computer scientists create more robust and reliable systems. In linguistics, the paradox has implications for the study of semantics, the branch of linguistics concerned with meaning. The paradox highlights the potential for self-contradiction in natural language and the challenges of defining meaning in a consistent and unambiguous way. Section 7. Taming the infinite solutions and workarounds. Mathematicians, ever resourceful, didn't simply accept defeat in the face of Russell's paradox. They devised ingenious solutions and workarounds to address the inconsistencies exposed by the paradox. One approach, known as Zermelo-Fraenkel set theory, ZF, restricts the comprehension principle, which allows us to define sets based on properties. ZF set theory avoids Russell's paradox by only allowing us to form sets from elements that already exist. In other words, we can't define a set based on the property of not containing itself, as this would create a circular definition. Another approach, called type theory, introduces a hierarchy of types, with each type representing a different level of abstraction. Sets are assigned types, and sets of a given type can only contain elements of lower types. This hierarchy prevents sets from containing themselves, thereby avoiding the paradox. These solutions, while effective, come at a cost. They introduce limitations and complexities that weren't present in naive set theory. Nevertheless, they demonstrate the ingenuity of mathematicians in addressing foundational problems and ensuring the consistency of their systems. Section 8. The paradox in the digital age, AI, and the unexpected. In the digital age, Russell's paradox takes on new significance as we grapple with the development of artificial intelligence. AI systems, like naive set theory, can fall prey to self-referential loops and unexpected consequences. Imagine an AI system tasked with designing a new programming language. This AI, if not carefully designed, could create a language susceptible to the same type of self-contradictory rules that plagued naive set theory. Understanding the principles behind Russell's paradox helps AI developers anticipate and mitigate such risks. Furthermore, the paradox highlights the importance of clear definitions and unambiguous language in AI systems. Just as Russell's paradox exposed the ambiguity of naive set theory, poorly defined concepts in AI can lead to unexpected behavior and unintended consequences. Section 9. A universe of paradoxes. The journey continues. Russell's paradox, while mind-bending, is not an isolated anomaly. It's a gateway to a universe of paradoxes that challenge our assumptions and push the boundaries of human understanding. From the liar's paradox, this statement is false, to the unexpected hanging paradox, these puzzles force us to confront the limits of logic and the slipperiness of language. More than a century after its discovery, Russell's paradox continues to fascinate and inspire. It serves as a reminder that the pursuit of knowledge is an ongoing journey, fraught with unexpected twists and turns. Embrace the paradox, for it is in the face of contradiction that we often discover the most profound truths.